We are talking about these covalent molecules and how they are sharing electrons, how they're attached together, these different atoms. So let's take a look at the angles and the shapes that these molecules take on. So just to remind you what an angle is, if you have two lines, so if you have three dots, you have a line connecting these two dots and a line connecting these two dots, and the angle is how far apart these lines are. So this would be the angle. I'm trying to make this about a 120-degree angle. Some people get confused and they point like from the dot to the dot and they say that this is an angle, but that's not really an angle. So it's the opening between two lines. So you need three dots and two lines to make an angle. And then a circle, remember going completely around a circle is 360 degrees. And so if you are going just halfway around a circle, this would be 180 degrees. If you're going a quarter of the way around a circle, this would be 90 degrees. So just a little quick review on angles there. So we have this valence shell electron pair repulsion theory. I think I have the letters wrong here. And that is a theory that says that these electrons, since they're negatively charged, are going to push as far away as possible. So these electron regions are going to try to be as far away from all the other electron regions. And what regions include are bonded atoms and lone pairs. So when we are trying to decide the shape of this particular molecule, we want to know this angle between these two lines. So we want to know how far apart this central atom has to hold its electron regions. And this is why it's important to count the bonded atoms, not the bonds. The carbon is holding on to two oxygen atoms. It does have four bonds, but these four bonds cannot separate as far as possible away from each other, because if these bonds tried to spread out far apart, then how are they going to both reach the same oxygen atom? That's not possible. So these bonds, even though they are all negatively charged and they repel each other, they don't really have a choice. They have to connect to the same oxygen atom, so they have to sort of be in the same place. But they don't have to be next to this other electron region. So this electron region and this electron region are going to spread out as far as possible. So the regions for this molecule are the bonded atoms on carbon, so on the central atom, which in this case, carbon has two bonded oxygen atoms and it has 0 lone pairs on it. There are other lone pairs on other atoms in the molecule, but that is not what we're counting. We're counting the 2 atoms and the 0 lone pairs on carbon, so this carbon has to make room for 2 regions. And as far apart as it can get the 2 regions is 180 degrees. If it gets any further, then they'll be closer in the other direction. So that's as far apart as they can get. So here is another example of a linear molecule. We have this beryllium holding on to 2 fluorine atoms, and it has 0 lone pairs. So it has 2 regions, 2 atoms, and 0 lone pairs. And so we end up with 180 degrees, a linear shape. So it's almost like a pizza cut in half. We have 180 degrees as the angle, and it's a linear shape. So it's almost like a pizza cut in half. The boron is trying to hold these 3 hydrogens as far apart as possible. So the farthest apart it can hold them is 120 degrees. So this boron has 3 regions because it has 3 atoms and 0 lone pairs. Here we have a carbon with 4 atoms and 0 lone pairs. And you might think that given this pattern, a pizza cut in half and a pizza cut in thirds, that you might have a pizza cut into quarters, which would give a 90-degree angle, but there's no reason why the molecule has to be flat. We can use 3 dimensions and we can get an angle that is larger than 90 degrees. So instead of a pizza cut in thirds, we have this tetrahedral shape. So it's kind of like there is a carbon in the middle of a 4-sided dice, and then the little corners of the 4-sided dice, the 4 corners that you have, are all the hydrogen atoms. So we have maybe a couple that are in the plane, these 2 are in the plane, and then if you can imagine part of this corner of the dice sticking into the screen and this popping out of the screen. That's what this dash and wedge line are supposed to indicate. This one's going back and this one's going forward. So we have a little four-sided shape here, each of these sides being a triangle. So this next shape with 5 regions is kind of interesting. We have a flat disk where the 3 things that are on the disk are separated by 120 degrees. So kind of like this thing over here. But then we have this skewer going through straight up and down. So we have this angle being 90 degrees. So between the skewer and any one of these dots on the pizza, you have a 90-degree angle. Between the dots on the pizza themselves, there's 120 degrees. So these are a little bit more spread out. These are the equatorial positions. If you think of this as a globe, here's the equator of the globe. So these are equatorial. Let's make them a certain color. I'll underline this in green to show that these 3 dots are equatorial. These other dots are axial positions. So the axial positions, you're a little bit closer to 3 of the dots. The equatorial positions have a little bit more room because you're 90 degrees away from 2 of the dots and 120 degrees away from the other dots. So these equatorial positions are a little bit roomier than the axial. So for 6 regions, we have an octahedral structure. So for this one, it's kind of like we have a pizza that is cut into fourths. We have 90 degrees in this pizza, and then we also have 90 degrees up and down. And so if you build this structure and you rotate it, you will not be able to find where the pizza is. This structure, you'll be able to tell that here's the stick and the other one's the pizza because there's not a stick going this way or that way. This one, no matter which of these atoms you hold up, you're going to think that you're holding on to the stick because all of these are even. So these, all the positions are the same. So everything is 90 degrees. Except if you go all the way across, you get 180 because it's 90 plus 90. So this dot to this dot is 180, but this dot to all the other dots is 90. These shapes are known as the electron geometries because this is based on whether there are 2, 3, 4, 5, or 6 regions of electrons in the molecule. So the examples that are in this chart have these regions all being atoms. None of them are lone pairs on the center atom. So the regions are atoms but not lone pairs. Sometimes you have one of these geometries, maybe tetrahedral, where instead of 4 atoms, you have 3 atoms and a lone pair. And the geometry is still tetrahedral, but it doesn't look exactly like the same shape. So let's go to another table where we can see if some of these regions are lone pairs, the geometry is going to be this geometry, but the shape is going to have a different name because it's going to look a little different. Here's the other table that I talked about. If the regions are all atoms, the shape has the same name as the geometry. But if some of the regions are lone pairs, then we have a different shape. So here we see when there are 0 lone pairs, the geometry matches the shape name. So we have trigonal planar shape, trigonal planar geometry. So these are the shape names for the compounds that we had in the previous table where we went over the geometries. However, when some of the regions are lone pairs, the shapes look a little bit different. There's a table in your textbook that has actual pictures of these shapes, and that is a little bit easier to see. I'll put that up in just a moment, but I have the names here at least so that you have them all in your note packet for reference. So let's go back to what I skipped by before, trying to get from one table to another. And that is an observation that you can have slight distortions in your shape. So if all of these electron regions were repelling each other evenly, more evenly than I can draw perhaps, a trigonal planar shape should be evenly cut into thirds, 120 degrees, because all of these electron regions are repelling each other. However, the lone pairs, if something is a lone pair instead of a bonded atom, it's going to repel more than repulsion between a lone pair and a bond. So lone pairs are going to repel each other the most. Lone pairs and bonds are going to repel a little bit less. And then bonds are going to repel less than that. This particular compound doesn't have any lone pairs as the regions, but it does have a difference in the size taken up by the bonds. So the lone pair again is repelling the most, it's taking up the most space, pushing everything the furthest apart. Then comes a triple bond, then comes a double bond, and then comes a single bond. So here in this molecule we have two bonds that are single, and then we have one bond that's a double bond. So let's go ahead and make this sort of a thick bond to show that it's taking up more space and it's pushing on things a little bit more. So since this bond is taking up more space and it's pushing a little bit more strongly away from itself, it ends up pushing these a little bit further, the hydrogen atoms. So this is going to be a little bit more than 120 degrees, and this one is also going to be more than 120 degrees, and then this over here necessarily is going to have to be less than 120 degrees. So instead of having even thirds for your pizza, you have two larger pieces and one slightly smaller piece. So this is what the formaldehyde molecule shape would actually be like because of these distortions. These hydrogens are being pushed a little bit away from the oxygen double bond and a little bit closer to each other. All right, so let's draw Lewis structures of these compounds. A lot of them are ones that we've seen before. And then we will look at how many regions are around the central atom and predict the geometry and the shape. So here is our ammonia molecule. Nitrogen has 3 atoms that it's attached to and a lone pair. So we have 4 regions, which means that the geometry is tetrahedral. But since one of these is a lone pair, this is called a trigonal pyramidal shape if you look at that table up above. Something that has 4 regions, one of which is a lone pair. The shape for that molecule is called trigonal pyramidal. All right, so here I've drawn this water molecule over here. The oxygen has 2 hydrogens bonded to it, and it also has 2 lone pairs. So this also has 4 regions, and it also has a tetrahedral geometry. And this one has 2 lone pairs, so that means the shape is called bent. So this carbon dioxide molecule we mentioned at the very beginning of the section, the carbon is bonded to 2 regions, and since 0 of these regions are lone pairs, the shape and the geometry are the same. So it is a linear geometry and a linear shape for this molecule. So this next molecule over here makes for a little bit of a challenging Lewis structure. We have these 2 possibilities as Lewis structures. They both have the correct number of valence electrons. However, if you look at the formal charges on the atoms, you will see that this structure is better than the one on the right. It does have a hypervalent sulfur, but sulfur is capable of being hypervalent, and so it can have 2, 4, 6, 8, 10, 12 electrons around it. That's not a problem, and the formal charge on the sulfur is 0 in this case rather than a +2 in this case. However, either one of these structures would have the sulfur with 4 regions around it and 0 lone pairs, so even if you had drawn this Lewis structure, you should get the same correct answer for the shape and the geometry. The 4 bonded atoms make 4 regions, which gives it a tetrahedral geometry. And since none of them are lone pairs, this would also be a tetrahedral shape. All right, so this is also a fairly interesting Lewis structure. This one we have 5 regions. The iodine has 3 bonded atoms and 2 lone pairs. So we have a trigonal bipyramidal geometry, but we do not have a trigonal bipyramidal shape because there are some lone pairs. There's 2 lone pairs, and if we check that table up above, the shape that's made with these 2 lone pairs, the 2 lone pairs take those equatorial positions, because remember, we mentioned those equatorial positions are roomier than the axial positions, so they take the pizza positions, they're around the pizza, and that gives these guys the stick and the other pizza one, so these are 90 degrees apart, and this gives it a T shape. I wanted to encourage you to take a look at the simulations for the shape and polarity that we're learning about. It's in our week 10 module. So this first one listed is the one for shape. Go ahead and check the boxes for the molecule geometry, or this is what we're calling the shape. This is the electron geometry, which we're calling the geometry. We can show the bond angles also. So here we have something with two regions, and it's a linear shape. If we have three regions, all three of them being atoms, it's a trigonal planar shape and geometry. If we have three regions but one of them is a lone pair, then the electron geometry is still trigonal planar. We still are showing the 120-degree angle, but the molecule shape name has changed to bent. And then you can remove things, put more things here. I'm trying to get the 5 region trigonal bipyramidal geometry and shape over here. So you can tell that these 3 equatorial positions are spaced out a little further than the axial positions. You have 90 degrees and 90 degrees. If we kind of move this down, you can see that you have 120 degrees around these 3. So you can tell that there are 2 of these groups that are right across from each other as a stick, whereas none of these 3 have something right across from them. So you can tell the difference between the axial and the equatorial positions. If we have a lone pair, it takes that equatorial position, so then it makes this sort of a seesaw shape. If we have 2 lone pairs, they both take equatorial positions, and then we end up with this kind of T shape. So this is cool to play around with the different shapes and the different geometries that we have looked at. Here's one on molecule polarity. We already looked at the 2 atom simulation when we were looking at just a specific bond between something with more and less electronegativity. 3 atoms is unfortunately as high as the simulator goes. It probably gets pretty complex. So we can show the bond dipoles, and we can also show the overall dipole, which is in yellow. So the bond dipoles are in black, and the overall is in yellow. So we have both of these. Both A and C are less electronegative. B is more electronegative, so it's pulling electrons away from them. However, if the shape becomes more and more symmetric, see how this yellow molecular dipole is starting to go away. And we start to have an overall nonpolar molecule. And when we put the electric field on, there's not nearly as much of an effect as if you have that molecule dipole. It attracts one end of the molecule rather than the other. If you have this asymmetric shape, but you have nonpolar bonds, then we don't have any attraction to the electric field. Overall, there is no molecule dipole. This molecule is nonpolar. So you can play around with that as well and take a look at polar and nonpolar bonds, symmetric and asymmetric shapes, at least as far as 3 atoms in a row can be twisted around. And then you can take a look and see how the overall polarity of the molecule is affected. We already have covered polar versus nonpolar covalent bonds. However, a molecule can have polar bonds and still be a nonpolar molecule if it's a symmetric shape. So if a molecule has all nonpolar bonds, then all of the electrons are evenly distributed around that molecule. And so no matter what shape it has, it's not going to be a polar molecule. By polar molecule, we mean that one end of the molecule has a little bit more negativity than the other. So here I've tried to make a diagram of a nonpolar molecule where the electrons are spread out evenly all around the molecule and there's not really a negative or a positive side. Whereas a polar molecule, we have more electron density on one side than the other. So we have a slightly positive end of the molecule and we have a slightly negative end of the molecule. So in order to get a polar molecule, you need both polar bonds and an asymmetric shape, because that will make the molecule uneven with its electron distribution. If you have nonpolar bonds, then the electrons can't really be uneven because they're being shared evenly all throughout the molecule. And if you have polar bonds but a symmetric shape, then the electrons are being pulled because they're polar, but if they're being pulled evenly in all directions, you're still going to get overall an even distribution like this nonpolar molecule. You have to have bonds pulling more in one direction, and you have to have those bonds arranged asymmetrically throughout the molecule in order to get this overall polar negative and positive end molecule. So let's compare this with some flat molecules on the screen. Let me write down the electronegativities for carbon and oxygen. You may recall from earlier in the chapter that we said that a carbon-oxygen bond was a polar bond. We have this oxygen pulling electrons away from carbon. We have a little bit of a dipole here. However, on the exact opposite end of the molecule, we have another oxygen which is also pulling electrons away from the carbon. And both of these pulls cancel each other out. We have a symmetric molecule. So we have polar bonds, but a symmetric shape. So this makes for a nonpolar molecule. We don't have a positive and a negative end. We have the electrons being pulled evenly in both directions. In contrast, this molecule still has oxygen pulling some electrons away from carbon. However, there's not an oxygen at the other end pulling in the opposite direction. So we have an asymmetric shape here, or a certain asymmetry to the molecule. And so overall, let's draw the overall dipole in a different color. Overall, this molecule has a dipole pointing towards the left. We have some more electron density over on the left side of this molecule and necessarily less electron density on the right side. So overall, we have a negative and positive end of the molecule. So we have a polar molecule here. Here we have nonpolar bonds. We have boron with a 2.0 and hydrogen 2.1 electronegativity. So we have nonpolar bonds. So any shape would really make this molecule nonpolar. But we do have a symmetric shape. So even if these hydrogens were all chlorine, something else that's more electronegative and would pull away from boron, they would all be pulling evenly in every direction. So it's a symmetric shape. So this is nonpolar. And this is a symmetric shape because this is flat. All of these hydrogens are pulling in, or they're not pulling, but if they were something that was pulling, they would be pulling in all different directions evenly. This over here is not flat. This is a trigonal pyramidal shape. And so we have these polar bonds with nitrogen being 3.0 and the hydrogens all being 2.1. We have some poles that are going in toward the nitrogen, but they're also going slightly up. So if you think of this as a pyramid sitting on a table, the hydrogens are all corners at the base. And so instead of pulling in towards a dot that's also sitting on the table, they're pulling in towards the apex of the pyramid. And so they're pulling in towards the middle of the shape, but they're also pulling up. So overall, we have the poles canceling left to right and front to back, but not up and down. We do have a little bit of a dipole that is going up the electrons are all being pulled up and there's no corresponding pull down to counteract that. So this is an asymmetric shape and a polar molecule. So here we have carbon versus chlorine, a very slight pull by chlorine, just a little bit more than the 0.4 cutoff. And so the slightly polar bonds are all pulling electron density away from the central carbon. But again, if you picture that four-sided dice with the carbon in the middle, it's being pulled evenly toward all of the points on that dice. So it's not like one side of the dice is, or one side of the die is more negative or positive than the other. So we have polar bonds, but we have a symmetric shape. So overall, these dipoles are going to cancel. We don't have an overall dipole. So this is a nonpolar molecule because of its symmetric shape. In contrast, if we only have two chlorines pulling on the carbon and these other hydrogens not pulling on the carbon because they are pretty close to carbon, then we have an up pull and a slightly down and to the left pull, but we don't have a down and to the right pull to counteract that. So we have an overall pull kind of up and to the left here. So we do have an overall dipole to the molecule. So we have a molecule with a slightly positive end over here, down and to the right, slightly negative up and to the left. So we have polar bonds and an asymmetric shape making a polar molecule.